Hi, I'm Stefan, and it is my pleasure to present to you LISO, a new method for Lidar-only self-supervised 3D object detection. As the title already suggests, the goal of this work is to detect 3D bounding boxes in LiDAR data using no human annotations. Red here is the ground truth, i.e. the goal of what we want to achieve, and depicted in yellow are the predicted 3D bounding boxes generated by our method. Now you might ask why this is relevant. One answer might be that annotating data correctly over time with all these fine details is very time-consuming and expensive, even error-prone due to the complexity and monotony of the task. At the same time, raw data is cheap and it makes sense to leverage it as much as possible. Before going into the details, I would like to give a brief summary of what we are about to see. In summary, our method works by generating some initial pseudo-ground truth of moving objects using self-supervised LiDAR scene flow. We then track and refine this pseudo-ground truth and use it to train an off-the-shelf 3D object detector. The single-shot detector generalizes from moving to movable objects, since it is not given any motion cues as input. We then repeat this cycle of inference, tracking, pseudo-ground truth, generation, and retraining. First, I would like to talk a little bit about what scene flow is. So given two consecutive point clouds, scene flow refers to the motion estimate between these two consecutive point clouds, going from one point cloud to the next point cloud. From the sensor's perspective, scene flow is caused by two phenomena. One is the sensor ego motion, which will cause uniform scene flow across the static background objects, like trees, houses, etc. And the other is dynamic objects that move on their own, giving a distinct scene flow. We obtain self-supervised LiDAR scene flow by using the off-the-shelf network SLIM for this. Additionally, we use KISS-ICP to generate LiDAR odometry, as demonstrated here by these accumulated LiDAR point clouds. If we then correct the LiDAR scene flow for the ego motion, this is basically what we end up with. Note how the colorful dynamic points stick out from the static background. In the next step, we generate initial pseudo-ground truth by clustering, box fitting, and tracking. We use dbScan to cluster the points and the scene flow in 6 dimensions and fit boxes around each cluster. These initial bounding boxes are then tracked over time using the ego motion and the LiDAR scene flow in the process. All detections are propagated forward using the scene flow and matched to new detections. Unmatched detections are propagated once into the future. We do this forward and reverse in time, combining and connecting tracks. These tracks are then optimized. Firstly, the positional jerk is minimized. Then, the rotations of the individual boxes are aligned with the track, and the median box size is used to combat over and under segmentation by the clustering. Too short tracks are discarded. Now we have obtained initial pseudo-ground truth of moving obstacles. However, we are interested in all potentially moving objects. So, we train an off-the-shelf LiDAR object detector on this initial pseudo-ground truth. We repeat this process for k rounds. The LiDAR object detector only sees single-shot point clouds and pseudo-ground truth, i.e. it has no concept of motion. Thus, it generalizes to movable objects over the course of the training, which can then be tracked and refined by the same mechanism as seen previously. At the beginning, the pseudo-ground truth contains no static objects at all. But then, over the course of the training, this improves further and further. For our experiments, we use the SLIM network for self-supervised LiDAR scene flow and extend it to 120 meters range. For the object detection networks, we use Centerpoint, a convolution-based architecture, and we also use Transfusion-L, a transformer-based architecture. We conduct experiments on the Waymo Open dataset, Argoverse, NuScenes, and Kitty dataset, using the same hyperparameters for each and all experiments and datasets. We compare against strong baselines. For more details, please refer to the paper. On all of the datasets, we outperform our baselines by a considerable margin. We also train supervised versions of the networks and discover that there is still a gap towards the self-supervised case. We close the presentation by showing you some qualitative results. This concludes the presentation, and thank you for your attention.